Hello everyone, welcome back to ptet.chemistry channel. So my name is Mr. On, and at the start of this year 2021 I've just been redeployed to teach at secondary level. So in this lecture tutorial, which will from now onwards be called lectorial, so it's short for lecture tutorial, I'll cover this topic 1 for the 2023. This is from the year 2023 for the 5070 O-level chemistry. This is a pure chemistry curriculum, so you will see a lot of overlap if you are doing a IGCSE extended curriculum, or if you are doing the Singapore O-level Cambridge examination. You will see that despite the different syllabus code, a lot of the chemistry contents are actually very similar for any 14 to 16 years old chemistry learners wherever you are all around the world. Like I said, whether you're doing the GCSE, which is the British the local British curriculum for the for the 14 to 16 years old category, or whether you're doing the IGCSE, which is the international equivalent of the British GCSE curriculum. Anyway, so let's get started with this. So I've just outlined, so this is what I use in my class for my lesson notes. So if you're actually one of my students, you can use this lectorial for recapping what you might have missed from lesson, or just to revisit some of the stuff that you might have forgotten from time to time, because it's important in chemistry not to just learn things at that point, at that moment in time. It's important to revisit ideas every now and again to reinforce your memory. Okay, that's how learning chemistry becomes more meaningful rather than a torturous moment for a lot of learners at this level. So these are the learning objective. So each of these learning objective is what you might have heard me referring to as the syllabus. So these are straight from the syllabus published by the Cambridge curriculum, published by the Cambridge International Examination. This is for the exam from 2023 onwards, so the exam from 2021, 2022 might be slightly different from what you expected to know for this particular year group who are going to sit for the 2023 O-level chemistry curriculum. So we need to be able to state the distinguishing properties of solid, liquid and gases. Distinguishing means differentiate. Can you tell the differences? Okay, can you identify from the differences from their properties whether it's solid, liquid or gases, which are the three states of matter? You also need to describe their structures of these particles. All right, so we are talking about particle, which is at the molecular level. We're not talking about the solid that we see, the liquid that we see, or the gas that we see, but we are thinking in terms about their particle separation. How far apart are they? We're talking about arrangement. How are they being packed? Okay, as well as motion. How are they moving? Okay, and then 1.1.3 is to do with describe and explain. So describing is just saying increase, decrease, higher, lower, up, down. Explain, so describe and explain means you need to know it in terms of in fact it relates to 1.1.4. we're talking about heating and cooling curve in terms of this kinetic particle theory, and in doing so, when we see this heating and cooling curve, we interpret it, we describe it. All right, because heating and cooling curve will show you the changes of state, okay, in terms of these particular terminologies that you need to master. There's a difference between boiling and evaporation, which I will highlight in a little bit, and these are all in terms of kinetic particle theory. Kinetic particle theory means you have to talk in terms of particle. I'll also talk about that in a little bit. 1.1.5 is to do with, again, in terms of kinetic particle theory. So all of this is to do with kinetic particle theory. How does the volume of a gas is affected by temperature and also pressure? Without further ado, if we go straight to kinetic particle theory, kinetic there refers to kinetic energy. So we know that kinetic energy is to do with motion, so it's to do with the motion of particle. All right, so the particle there, so there's also to do with energy, of course. Yeah, so the particle there refers to not what we see. All right, it refers to the particle which we don't see. All right, everything is a model. Okay, it is a theory, so they're always moving, and and it's the property of the three states of matter as well as the changes of state that actually govern the chemistry that you'll be learning, because chemistry is the study of matter, and everything around us is made out of matter. So matter is anything that has mass and occupies space. Okay, so you might have heard of matter as anything that has mass and occupies space. There are three states of matter: solid, liquid, and gas. This is the structure, so it's a representation of the particles. What is important, if they give you empty boxes, the common misconception or the common mistake really is that people draw different sizes of the particle. If you're talking about pure substances, if there's only one type of the solid, all of them should be of the same size. Okay, only one type of liquid, they should be of the same size. Only one type of gas, they should be the same size. All right, we represent them in two-dimensional. That's why they are drawn as circle instead of sphere. Sphere is a three-dimensional structure, circle is a two-dimensional structure, and this is a two-dimensional picture. All right, so here you will see that they are touching each other. That's because it's tightly packed. All right, tightly packed is also known as compact. Okay, so we don't talk of solid being closely packed, because if you just say solids are closely packed, it is closely packed, but they are closely packed much more than liquid, and it's much better not to use the word closely packed. Instead we use the term tightly packed, and it's very important to differentiate tightly versus closely. Okay, because you see here is packed closely, not as tight as in solid. All right, so this is arranged in an orderly manner. This is important. Orderly manner means you see they're arranged in like a fixed array of lattice, whereas here there's no regular arrangement because some of them are up, some of them are down, but there's a little bit more space in between, even though they are still touching each other. Some of them are not touching as much as others, okay, but that's because they are not packed as tightly as in solid. The important thing about gas is that it's not enough to just say that gas is not tightly packed, gas is not packed closely, okay, or gas is not touching each other. It's not good enough. All right, you have got to mention or specify that gas are very far apart from each other, as you could see. Okay, there's a lot of separation between the gas particles. So this is the first and most important thing that they like to ask. The second bit is to do with movement. The other thing mentioned in the syllabus was on motion, so that could be one of the things they ask you. So the important thing about solid is that we talk about fixed position, we talk about vibrate. So solids do not move randomly, they only vibrate about fixed positions, and liquids do not move randomly as well, they slide past each other. Liquids do not vibrate about fixed position. You need to be aware of this, because due to the separation, due to the little bit of space between the liquid particles, they can slide past each other. But in solid, because everything is touching each other, there isn't really much room for you to move around, even a little bit. Therefore, you can only vibrate about fixed position. For gas particles, they move freely. The other word you can use is to do with randomly. A lot of students, they will remember to put down move freely or move randomly, but they forget about the ideas of high speed. All right, so this is vibrate about fixed position. This is actually low speed. Okay, I write low speed, but it's actually not moving very much. So in terms of speed, when you go from solid to liquid, their speed will increase because they are moving more, and their speed increases a lot because the gas particles can move or they can roam randomly at very high speed. All right, so the kinetic energy of the particle increases from solid to liquid to gas, and you will lose the kinetic energy on going from gas to liquid to solid in this backward direction. Yeah. In terms of shape and volume, they are also commonly asked in questions, although not as common as packing or motion of particles, or in terms of the energy of the particles. That's to do with their motion. What kind of motion do they have? Are they just vibrating? Are they just sliding past each other? Or are they moving randomly at very high speed? Okay, but that doesn't mean that shape and volume are not important. As we know, solids are not compressed easily, but gas can be compressed easily when you think about stuff like liquefied natural gas. So a lot of countries are still using liquefied natural gas in their cooking cylinder, although some people have moved on to use electricity, which is obviously cleaner. But electricity also comes from burning hydrocarbon or fossil fuels such as this liquefied natural gas. All right, it's called liquefied natural gas because the gas is compressed, because gas can be compressed. It's compressed under pressure, so you make the gas particles move closer together. As you apply pressure, you make them closer together. Because the gas particles are closer together, they can be liquefied, they can be condensed. Liquefied natural gas means the gas undergo condensation. This is section 3 on changes of state, one of the key areas identified by the syllabus. Each of these terms you are supposed to know what they means. All right, so solid to liquid is a change called melting. Liquid to solid is called freezing. Liquid to gas, here they call it boiling or evaporation. Usually boiling only takes place at boiling point, only at the boiling point, whereas evaporation can take place at any temperature. So as long as you have a liquid, some of the liquid particle will have enough energy to escape and become the gaseous particle, okay, but not all of them. Whereas when you boil the whole liquid can eventually turn into gas, whereas that's not true for evaporation, because only a few particles on the surface of the liquid will have enough energy to escape and vaporize and turn into a gas. That's the main difference that you have learned from your lower secondary or your whatever basic sciences that you have learned before you turn 14 years old and enter this upper secondary level. Gas, on the other hand, can condense into liquid in a process called condensation. These two processes are less known, but there are some solid that can turn straight into gas. An example is iodine. So the molecular formula for iodine is that it exists as I2 molecule. As a solid, this is a gray black solid. It looks more like gray rather than black. When you heat it, it will go to I2 gas, and it still maintain the entity, the identity of the molecule, but then you will see a purple gas being produced. So that is sublimation. The other one, which is very common, is something called dry ice. If you have seen stage performance, they use dry ice to produce the smokiness, okay, the white color smoke, you know. So it's completely harmless because it's just carbon dioxide that, you know, we are breathing out. We are just introducing more and more carbon dioxide from the sublimation of the dry ice. So it creates a dramatic effect in a stage performance. And we use dry ice for packing a lot of things that we want to keep cold as well. So some stuff, if I'm not mistaken, some of the COVID vaccine, so COVID 20, so COVID 20 was a big thing back in 2020, and some of the vaccines had to be kept at a particular temperature. If you want it to be very 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 cold, you can keep it with dry ice, you know, where you keep it, you know, at low temperature, or they could keep it with liquid nitrogen depending on what kind of storage they want to keep the vaccine at. Yeah, but it will help to keep something cold. That's called sublimation. That's the process. And gas going to solid is just deposition. Heating and cooling curve are very very important. So you will see that the solid is actually where the temperature is increasing. So this is a graph. The y-axis is the temperature. The y-axis is what you measure. So what you measure, and what you measure is called dependent variable. So if you are going to stay in sciences for a long time, you need to know that there are certain things in an experiment where here this is the x-axis, and the x-axis is what you change, and what you change is called the independent variable. So variable means things that can affect the result of an experiment, and two different kind of variables. One is dependent, one is independent. The dependent is what you measure, which is on the y-axis. Easy way to remember. So a good friend of mine taught me a couple of years ago. So the idea is to remember, why are you so dependent? Why are you so dependent? Why are you so dependent? So y-axis, The vertical axis is the dependent variable, is what you measure. As you change the x-axis, which in return, because this is the why you so dependent, so x is the independent variable. There are two important bits to this graph, one of which is to do with the change of state. So the change of state only takes place at the particular temperature, because pure substances meaning it has got no impurity, so pure substances melt and boil at a fixed temperature. So that there is only one single value for the melting point, and there is only one single value for the boiling point. They are not equal, but there's only one value for this and one value for this. These are temperature, and this is temperature. That's why melting point and boiling point are labeled on the y-axis and not on the graph. Okay, as some of you would have mistakenly done. Melting point is the temperature at which the solid melts. The solid turn to liquid. All right, that's why you have both solid and liquid, because this is the change of state. The horizontal line there is the change of state. That's why you have both solid and liquid. Boiling point is the temperature at which the liquid boils. Liquid turns to gas, liquid boils. That's why you have liquid plus gas. Again, this is the change of state. This is the change of state. This is liquid to gas. This is called boiling, not evaporation, because this is not happening at any temperature. Evaporation can happen at any of these temperature, but when you are here, there's only one temperature at which it boils, because pure substances melt and boil at one fixed temperature. Each one has their own value. Yeah, this is solid going to liquid. This is solid going to liquid. This is called melting. The states of matter refer to, is it a solid here, solid and liquid, liquid here, liquid and gas, and also gas just being here. Okay, when you are talking about change of state, the change of state is melting, but the states of matter are solid and liquid. The states of matter are liquid and gas. The change of state, meaning the process, is called boiling. States of matter is not the same as the change of state. They are two different things. Make sure you know the differences between the English language they are being used. Alright, so make sure you also read the question what are being asked as well. Right, as I mentioned previously, there are two parts to the graph. The first bit is to do with this vertical increase. Alright, this line, pink line is where the heat energy is supplied. So your heat energy supplied, where is it going to? The heat energy supply is going to kinetic energy of the particles increases. So you are continuously supplying heat. Why? Because this is called a heating curve. It's called a heating curve. That's why the temperature is going up. If you see the temperature is going up because you are supplying heat. Here, the heat that you supply goes to increase the kinetic energy of the particles. Okay, there's the conversion of the energy. So the solid particles are moving faster. In fact, they are vibrating faster. So vibrate faster, but not moving further apart. So they are still tightly packed. Why? Because we are still talking about solid. Have they melted yet? No, because you are still below melting point. So why would they melt? That's why this is solid, because the temperature is still below the melting point. This is the start of the melting point. At the start of the melting point, you start to melt. When you start to melt, you don't straight away become liquid. Your solids start to melt. Your change of state is happening. Your temperature is not changing. Why is your temperature not changing? Because your temperature is not changing because, so that is 1 and this is 2. So the heat energy is still being supplied, but where does the heat energy go to? The heat energy goes to break forces of attraction. Okay, forces of attraction between something. If you are talking about melting, so you're going from solid to liquid, so you need to separate the solid particles that are tightly packed. You need to separate them so that they become closely packed but with a little bit more space in between. That is the model that you already have it in your mind. You need to separate them a little bit so that you create a bit more space in between so that they can slide past each other and not just vibrate about fixed position. To separate them, you need to break the force attraction between the solid particles, and that is where the heat energy supplied goes to. Do you move faster during change of state? So no change in speed. There is no change in speed here because there is no change in temperature. Temperature is a measure of kinetic energy. So I'm not sure how you were taught back in lower secondary, but you will have learned in physics in this upper secondary level. Temperature is a measure of the average kinetic energy of particles. So if no change in temperature, that means no change in kinetic energy. That means no change in speed. So you are not moving faster at this horizontal line, because here you are moving faster because temperature is increasing, and temperature is a measure of the average kinetic energy. So as temperature increase, kinetic energy increase, speed increases. The solid particle vibrate faster because they are still tightly packed, but they are not moving further apart. They are just vibrating faster. Here they are not vibrating faster. Okay, they already reached the optimum speed of vibration here. So all the heat energy supplied goes to break the force of attraction between the solid in order for you to become liquid. Because this is what you are doing, that means there is no conversion of the heat energy into kinetic energy. So you are not moving faster, but you are moving further apart. Okay, but moving further apart. So there's the difference between this line and this line. Okay, you can apply the same idea going here, because by the time you finish melting, there is no more solid because all the solid have already been separated and they now can slide past each other, and they now have more spacing in between but still closely packed. All right, they're all liquid particles, so the liquid particles can slide past each other at a faster speed. As temperature increases, they can do that a bit faster, but they behave like a liquid. All right, they are not moving far apart. No, because this is just changing kinetic energy. At this second horizontal line, you are doing another change of state. So there's no change in kinetic energy because the liquid particles are not moving faster. Instead, the heat energy that you supplied is being used to separate the liquid particles even further apart in order to become gas, because gas particles are very, very far apart. I'm sure you know this table by now. This table is as stated in the syllabus. Packing and movement for solid, liquid and gases, all of these are in the syllabus again and again and again. All right, by the time you finish boiling, okay, so then any heat energy supplied goes back to increasing the kinetic energy. So the gas particle move faster again. Okay, so the gas particle move randomly at very high speed here, and they just increase in their speed because temperature increases, but there's no further change of state because all of them have already boiled, all of them have already turned into a gas. So gas particles, okay, can only be obtained at a higher temperature. So gas particle will have a lot more kinetic energy than liquid particles, than solid particles, and as such gas particle will move at a faster speed, okay, randomly in all direction, whereas solid particle can only vibrate about their fixed positions, where they are tightly packed together. So heating curve, a lot of information you can interpret from it. Based on what I said, I know this is a very summarized condensed note, but based on what I said, you can put it into your own word and try to extend this paragraph a little bit more. Okay, describing this as well as explain as stated in the syllabus. Describe and explain, I talk about the two different kind of energy changes in terms of the change of states of matter, in terms of what you are doing, in terms of the definition of temperature, as well as kinetic energy. The next bit is the opposite of heating curve. This is a cooling curve, all right? So this is a cooling curve showing all the way from gas to liquid to solid. As you can see, there is one step down, two step down, all right? In the question, they can just show you a one step, which is from gas to liquid, or they can show you liquid to solid as a one step, okay? When it's a one step down, you cannot have gas, liquid, and solid, yeah? It's just from one form to another. But of course, the question can also show you the whole of the cooling curve, and cooling curve is when the temperature goes down, as you know, as you expect from cooling. Temperature goes down. It's still temperature on the y-axis being the dependent variable. Y-axis, why are you so dependent? X-axis, independent variable. And because you're cooling down all the way from gas, okay, so this one they have labeled it with boiling point, but it's actually the same as condensation point. Okay, so condensation point is just another value for is a temperature for which gas condenses into liquid, is equal to the boiling point when liquid turns to gas. As you imagine in the previous heating curve, when liquid turns to gas, it's a fixed temperature called the boiling point. When you go backward, it's like a reflection in the y-axis. It goes down, this is the condensation point, and it goes down, this is the melting point, which is the same as the freezing point, because melting is going from solid to liquid. That is equal to the freezing point, which is going from solid to liquid. All right, so that's why I've written it down as melting point, but that is equal to the freezing point, which is the opposite change of state. Again, the change of state is when there is no change in temperature. All right, so during changes of states of matter, no change in kinetic energy. No change in kinetic energy. So you are not moving slower. We are talking about moving slower because here you are moving slower, but still randomly. Why is the gas particle moving slower? Because temperature is going down. So that means your kinetic energy is going down, because temperature is a measure of your average kinetic energy of your particles. So your gas particle has lost kinetic energy. Your gas particle are now moving slower. Your gas particle have lost its speed, all right? But it's still a gas particle. They haven't moved closer together. They have just moved slower, all right? But still randomly. That's why I say it's still a gas. Whereas here you are no change in speed. Well, no change in kinetic energy means no change in speed, because there is no change in temperature. It only happens at one single temperature, all right? So what happened there is it will release energy. Previously, when we talk about heating curve, because heating curve was to do with boiling, so we need energy to break force of attraction between the liquid particles. Because we are doing liquid to gas, we need to prevent the liquid from being attracted toward each other. We need to make them far apart for it to become gas. We need energy to do this. Here you are making the gas particles closer together, so therefore when you form force of attraction. You form force of attraction between the gas particles, so move closer together. That's why the important idea here really is release energy, because this is cooling, so you release energy. You don't require energy, you will release energy. Same thing here, liquid plus solid, because here you have both liquid and solid. The freezing. During freezing, so your liquid particles will start to become more and more compact, okay? So your liquid particles move closer and become, so you previously you have some space. What happened now is you become tightly packed. This is called describing what happened from the liquid particle which can slide past each other. Now they just become tightly packed and vibrate about fixed position. So it's the changes from something to something else, okay? Whereas by the time you finish freezing, there's no more liquid. That's why all of it is just solid, and the solid particles are just vibrating slower. That's why your temperature is going down and down, okay? So all of these basically outlines what I have just mentioned, so I won't go through this. You can get a copy of these notes either from your textbook or from whatever notes that your teacher will have supplied you, or from whatever summary notes that you can make based on what I just explained. So for those in my class, you can, for my very own students, you can of course read through this, but it doesn't mean that you shouldn't read your textbook, because previous experience told me that students don't like to read, and that is a big problem. So if you decide to stay in sciences, you have to develop a habit of more independent reading, and it starts from the very beginning. This is topic 1. If you want to go further, you need to cultivate a very good habit. When you read, you pick up some notes, and then you will try to turn away the page and write on a piece of paper, just like what I've done in all my lectorials. Like, look at the syllabus, think about what you need to elaborate, describe, and then you can check what you have read and see whether they are complete or not. You repeat the cycle day after day, a little bit at a time, and eventually, hopefully, you become an expert like me as well, okay? So this section 4 is the last bit of states of matter for this pure chemistry course 5070. So this is basically Boyle's law, and you will learn more of this in your physics. I don't know your physics component code. This is also Boyle's law, okay? So it's saying that PV is constant because P is inversely proportional to V. So PV is constant. So PV doesn't change with pressure. PV doesn't change with volume. That's why it's just a straight line, because PV equal to constant based on Boyle's law at constant temperature. Okay, so it's very important. Whereas this one is volume is proportional to temperature in Kelvin at constant pressure. So this is Charles' law. So both of these guys pioneered the development of these laws of gases based on a series of experiments. All right. So just to go through the idea, because what is important at all level is not really about the gas law, but it's about the kinetic particle theory. So you need to be able to explain it in terms of what happened to the particle. What happened to the particle, all right? So when you go higher temperature, we talk about temperature as a measure of your average kinetic energy. Particle will move faster, therefore they have more kinetic energy. When you move faster, you will collide more frequently. So a lot of students, they would just think about this, but they forgot to relate it to pressure when Boyle's law asks you about pressure on volume. Okay, so you need to relate temperature with pressure as well. Okay, so at higher temperature, because if they collide more frequently, they collide with the walls of the container. So pressure is force over area, force exerted over the area. This is your lower secondary science definition. Pressure is defined as force over area. You will learn this in physics again. The unit will be Newton per meter square, or you will express it in Pascal, which is Newton per meter square. Force, the unit is Newton. Area, the unit is meter square. Pressure is force exerted per unit area. Collide more frequently with the walls, exert more force on the wall, same area, greater force, same area, higher pressure. All right. And to reduce the pressure, then therefore it will occupy greater volume, because we are talking about constant pressure. So all of these are important to reduce the pressure or maintain the pressure. Therefore, it will occupy greater volume. I'm not sure if I should talk about expansion. Or maybe that's all right, I guess. Anyway, so Boyle's law on the other hand is to do with the gas volume being decreasing. For example, when you have a piston, so one of those gas piston or gas syringes that can they can move along, like increasing the volume inside the piston or decreasing the volume inside the piston. Again, it's to do with collision. Okay, it's to do with the pressure. Okay, so pressure, as I mentioned, is force per unit area. So when you decrease the volume of a gas, you also decrease the container wall area, and therefore they collide more frequently. Colliding more frequently means they exert more force over the same area, and therefore this will increase the pressure. All right. The last bit of this topic 1 is to do with diffusion. So describe and explain diffusion. So you need to know how to define it. So definition, they like to ask you for definition, either for 2 to 3 marks, and you need to think about it in terms of kinetic particle theory. Okay, so it's to do with particles. So this is your first point. It's to do with moving from a region of high concentration to a region of low concentration. Actually, that's to do with your second point. I forgot to add the first point is to do with particles move randomly. So it's to do with random movement of particles from a region of high concentration to a region of low concentration. So that is very important. Yeah, moving randomly, region of high concentration to a region of low concentration. And then we need to think about the factors as well. So the higher mass refers to relative molecular mass. Okay, so there is the mass for one, the relative molecular mass is a relative mass for one single molecule. So the lighter you are, the heavier you are, you will move more slowly. Moving more slowly means diffuse slower. Okay, so when you are lighter mass, you can diffuse at a faster rate because it's lighter. And in terms of explaining it, you need to talk about the MR. So must show and calculate. So basically must show your calculation to explain clearly, to explain or state clearly. So it's not enough to just say it's lighter, it's heavier. All right, so you need to actually specify your calculation, or at least give the value. You don't memorize this value because you could obtain this from the periodic table. The formula for ammonia is NH3. The formula for hydrogen chloride is HCl. Sometimes you're given the formula in the question itself. So I'm aware that in the periodic table that you have, what you have is you have 7 and 14 given in a periodic table like this. Hydrogen is 1 and 1, and then chlorine you have 17 and 35.5. Okay, so it's also given in a periodic table that something at the bottom, they call it the relative atomic mass. All right, so this is the one thing that a lot of students couldn't do very well at this stage because you are not used to formulas, but I assure you it will become more clear and explained in the next couple of topics, just in diffusion, without telling you the formula and getting you used to it. It's very difficult to ask questions on it because all the past year questions will have revolved around this kind of formulas and being able to work out the relative molecular mass. Big M, small r refer to relative molecular mass. So what are we talking about? The 3 there mean 3 times hydrogen atoms. No number there means 1 time nitrogen atom. That's why we don't show it. Okay, so this one mean 1 time hydrogen atom, and this one mean 1 time chlorine atom. This is the mass number. Okay, so this is the mass number shown in the periodic table is the number at the bottom. So the mass of one atom is 14. Well, the relative mass of one nitrogen atom is 14. The relative mass of one hydrogen atom is 1. The relative mass of one chlorine atom is 35.5. When you have NH3, you have one nitrogen atom. Each nitrogen atom has a mass of 14, close bracket. You add them together. We don't multiply, but we add because this is to do with what is the mass of this thing. It depends on the individual mass of the atom being summed up together. The mass of each hydrogen is 1, and I have 3 hydrogen atoms. You will have realized that here I have the number of atoms multiplied by the mass, but here I have the mass multiplied by the number of atoms. Because multiplication, when you have A times B is the same as B times A. So it really does not matter which order you do them in, as long as you have the correct number of atoms and you have the correct mass number as obtained from the periodic table, as obtained by reading the periodic table, as obtained by knowing your periodic table, as well as the symbol for the element. So that is very fast for you to work with. Okay, so this is a plus because you are adding the individual mass of all the atoms present in that molecule. That will give you 17. For HCl, for example, you will have one hydrogen atom, okay, and that continues to, there's one which is the mass of hydrogen, and then I have one chlorine atom, and there's 35.5, which is the mass of one chlorine atom. So they give me 36.5, and because 36.5 is heavier than 17, so 36.5 will diffuse slower. So this is heavier and this will diffuse slower. One of the common mistake that people will do, students will do, is that here they keep on talking about the relative molecular mass. Okay, when you use the word density, it is not correct here because density is mass over volume. So density is not mass, so do not have density is not mass. So do not use the term like ammonia is less dense than HCl, because density is not mass, and this definition have been taught to you in lower secondary. Okay, so this is what is meant by describe and explain the effect of the relative molecular mass. You see, they use the term relative molecular mass, so you have to use it based on the syllabus. On the rate of diffusion, we talk about heavier mass move more slowly, so that is in terms of the particles, and therefore you have slower rate of diffusion. If they have the same mass, they will diffuse at the same rate. Things like nitrogen, so nitrogen gas exists as N2, so nitrogen, the molecular mass of nitrogen will be 2 times nitrogen. The mass of each nitrogen atom is 14, so they give you 28. When you have carbon monoxide, so at this stage I can just give you the formula, but by the time you reach to the next couple of topics, you should be able to know this formula as part of your vocabulary. So this one means there is one carbon atom and there is one oxygen atom. Why? Because there is no other number that are being shown. Unlike this one has 2, that's why there are 2 nitrogen atoms. There are no number being shown, that means it's 1. Okay, if it is 0, we wouldn't even show the atom to begin with. Yeah, 12 times 1, because carbon in the periodic table is 6 and 12, oxygen is 8 and 16. So 12 times 1, and then I have to 8. 16 times 1, this is 28. So these two, they will diffuse at the same rate, and that is because they have the same relative molecular mass. The term is stated in the syllabus of which they say candidates should be able to from Cambridge. If you are not able to, well, unfortunately it means you have to learn until you are able to use the correct term. Okay, so yeah, I mean, I could go on and on, but ultimately it depends on your practice, and for more practice you can watch the checkpoint questions for how I go through several examples of past year paper questions on questions that involve the changes of states of matter, or even questions on diffusion as well. Alright, so thank you for watching, and I hope that was useful for a recap of any lessons you might have missed, or as a recap for your revision. And obviously you can skip through things you know, but you shouldn't skip through things that you don't know. Alright, so mastering each and individual statement of the syllabus is very important. It looks like very simple, the statement, but there's a lot of things that goes around in here. Describe and explain. So a lot of people are able to describe. No, actually, a lot of people are able to state. Stating means very short answer. Describe means you have to describe them in terms of the particle. Alright, and then obviously explaining is the one where a lot of students will struggle, because coming from lower secondary, you are used to everything being short answer, but everything in Cambridge exam is to do with the number of lines given as well as the number of marks available. The general rule of thumb is look at the number of marks. The number of marks tell you how many points of interest. Points of interest meaning useful point. Repeating the question is useless. Saying the same thing again and again is useless. So you have to understand why the question gives you that much mark for that much lines for that particular question. So thank you for watching, and ask me if you are my students if you got any questions, and I'll see you in the next video. So thank you for watching, and catch up with the checkpoint questions tutorial as well.